Did you know that adjusting the belt tension can improve print quality? Hi, we are ProRefied. In this video we will experiment to find out just how tight the timing belt should be on a 3D printer. Most 3D printer manufacturers tell us that the timing belt should not be adjusted too tight nor too loose. What exactly is too tight and what is too loose? According to the Drive Design Manual by Gates, belt installation tension is needed to cause the belt to conform to and mesh properly with the sprockets, and the amount of tension necessary for this is referred to as the minimum tension. Different belt types and widths have different minimum tensions. Take the common 2MRGT2, 6 mm belt for example. The minimum tension is 2 pounds. So how can we measure the exact belt tension on a 3D printer? Gates has a sonic tension meter that measures the frequency of the sound made by tapping the timing belt, and thus calculates the timing belt tension by formula. Such professional tools are not only expensive, but also inconvenient to purchase. But there is a popular method in the community that also uses this principle, using a smartphone app instead of a professional tool to measure the sound made by tapping the belt, which can also be used to calculate the belt tension. This method of measurement is described in the official Voron guide, which uses this minimum tension as an initial setting to avoid stretching the belts too tight. The Drive Design Manual by Gates also mentions a general value of 4 pounds for belt tension, which can be increased to double the value for higher position accuracy applications. In actual 3D printer applications, many will also choose a tension close to this general value of 4 pounds. For example, Bare Frame Upgrade gives a recommended reference value of 90 Hz. The tension of 5.2 pounds is calculated using the formula. Prusa's guide uses different approaches to measuring tension. One is to use a 3D printable tension meter to determine the belt tension by the deformation of the tension meter when stretched. The other is to determine the tension by measuring the motor load in the firmware. By testing the frequency of the belt in the extreme cases of these two methods, we have calculated the corresponding tension range. We have summarized these converted tension values in this chart. So how much belt tension should we use exactly? We decided to investigate the effect of belt tension on actual print results, in terms of print accuracy and print quality. Does belt tension affect print accuracy? To explore it, a test platform was set up to accurately measure the real-time position of the Y-axis using an optical linear encoder. To simulate the real printer as closely as possible, we have simulated the Y-axis of the original i3 Mark III's Plus, using the same timing belt spacing, restored the Y-axis arrangement and the original control board to drive the motor. We also restored the Y-axis weight. We tested the repeatability and dimensional accuracy of the movements with different belt tension using our test platform. We take a position as the reference point A, then move to a random point, then return to the reference point A and stop. The actual coordinates of each return from the random point are measured and recorded, and the difference between the maximum and minimum values is the repeatability. To measure dimensional accuracy, we simulated the movement of the Y-axis. When actually printing a cube, the Y-axis is moved back and forth between the specified positions, and each time it makes a trip between 2 points, it stops for a while before continuing to move. By recording the difference between the actual distance traveled and the distance of the G-code command each time, we can derive the percentage error of the dimensions. After repeating the measurements several times, we found that both repeatability and the dimensional accuracy decreased as the timing belt was progressively tensioned. Especially the dimensional accuracy. For example, a 2 pounds tension results in an oversize of approximately 0.02%, while a 6 pounds tension results in an oversize of nearly 0.1%. This can lead to an error of 0.2 mm on a 200 mm of travel, which is not negligible. After further experiments, we found that the dimensional deviation due to movement on the Y-axis was less on the side closer to the motor and more on the side further away. It is not uniform over the entire range of the Y-axis. In the test we also found at different travel distances, the dimensional deviation does not increase linearly as the travel distance increases. These two factors make it impossible to compensate for this error with a simple linear correction of the dimensions. Therefore, in terms of precision, we believe the tension of the timing belt should not exceed 3 times the minimum tension. Apart from accuracy, does the belt tension affect print quality? We can also explore print quality with our test platform. Many print surface imperfections are produced by uneven movement. When the extruder is extruding at a constant speed and the speed of the printhead fluctuates, the extrusion width will also fluctuate. By calculating fluctuations in printing speed based on the data from the test platform, we can calculate and derive the fluctuations in extrusion width. This allows us to quantify and study the problem in a more objective and precise manner. So we used G-code to control the y-axis of the test platform to move back and forth and use the data from the optical linear scale to calculate the actual speed of movement and thus simulate the print quality. When we change the belt tension, the print quality also changes. We analyzed the data using the FFT method to quantify the intensity of defects and found that the main defects that showed up in the test are those with 2 mm pitch and those with less than 1 mm pitch. In our experience, the 2 mm spacing ripple is mainly caused by the timing belt, while the one below 1 mm spacing is motor resonance rippling or MRR, which is mainly caused by motor vibration and is often referred to as VFA in the community. By comparing the strength of the frequencies corresponding to these two defects in the frequency spectrum at different belt tension, we found that as the tension of the timing belt changes, the strengths of both the belt rippling and the motor resonance rippling change accordingly. If we take into account the effect of the timing belt tension on both the two surface defects, we can obtain a better print quality by adjusting the belt tension so that the strength of both patterns is relatively low. At 4 pounds, for example, the belt rippling is reduced by 57.23% compared to it at 2 pounds, and the MRR is also reduced by 39.06% compared to it at 7 pounds. We also tested different motors. On the test platform, switching to a low vibration motor reduced the MRR by 76.81% under the same 7 pounds tension, and if we also adjust the belt tension to 4 pounds, we can further reduce the MRR by 28.2% and achieve a total MRR reduction of 83.35%. In summary, according to the test platform data, adjusting the timing belt properly can reduce the intensity of surface ripples to some extent, while upgrade to the low vibration motor with optimized timing belt tension will greatly reduce surface ripples and improve print quality. To verify this discovery, we tested the actual print quality on the 3D printer with different timing belt tensions. The print test confirms our findings. Fine-tuning the timing belt tensioning does improve print quality by reducing both MRR and belt rippling. The reduction in MRR is even much greater when we use a low vibration motor. Upgrading the motor and optimizing the timing belt tension at the same time did result in a very significant improvement in the final print quality compared to before the optimization. However, we also noticed that the variation in surface quality with tension in the actual printing tests was not the same as on the test platform. And for the original i3 we tested, the best overall results were obtained when the timing belt tension was around 4.2 pounds. This difference in surface quality in response to belt tension is most likely due to the different system stiffness and natural frequencies between the test platform and the 3D printers, resulting in different resonance behavior. This inspired us to adjust factors such as the weight of the test platform and the length of the timing belt to investigate the situations on other different printers. We have found that many factors can influence the vibration distribution at different tensions. For example, if we decrease the weight or try a shorter distance between the shafts with shorter timing belt, the optimum tension will increase. So in summary, although the optimum timing belt tension varies from one 3D printer to another, on each model we can still find the optimum timing belt tension within a certain range to optimize print quality as much as possible. To make it easier for the community to adjust the belt tension to optimum, we have created a guide, which can be found in the description below. We have also started a GitHub project to serve as a platform for sharing belt tension values so that the same printer model can be adjusted to the same tension for the best print quality. The link to this project is also in the description below. To further improve the print quality, a more effective method than just adjusting the timing belt is to upgrade to low vibration motors. We are Prorified and we have motor upgrade kits for the Prusa i3 Mark III and Mini series, as well as motor development kits for other machines. Each X and Y motor in the kit has been tested to ensure low vibration to improve the print quality. The link to our motor kits is also in the description below. And there is one more thing, by the way. The tension of the timing belt also affects ringing. A timing belt tension that is too low will increase the ringing amplitude as well as its duration and distances, so the timing belt should not be adjusted too loose. However, unlike the timing belt ripple and motor resonance rippling, ringing is directly caused by the acceleration and deceleration of the motion, which in turn can be directly controlled by the 3D printer. This is why ringing can be mitigated by input shaping. As our test platform can measure vibrations very well, we also used the test platform to try out G-code-based input shaping and successfully found a way to mitigate ringing using G-code in our attempts and iterations. This G-code-based input shaping has been proven to work in actual printing. Although this technology is still in its early stages of exploration, once this technology matures in the future, we will be able to output G-code directly via the slicer with input shaping applied, which has no limitation on the mainboard and no additional pi required. This could lower the barrier to high-quality 3D printing. For future updates, please like, share and subscribe.